I'm going to spend this whole video reviewing L'Hopital's rule. So what we did in 8.7, talking about some of the basics with L'Hopital, some of the algebraic ones, sometimes when you have to look at needing to do repeated L'Hopital, and then I want to finish with one of the logarithmic differentiation applications of L'Hopital. So everything in this video is going to be over that particular topic. So the first couple ones that you're looking at right here is just asking you to find a limit. First thing you want to do with your limits is just make sure that you can't do direct substitution. So for example, with the first one, when you look at it, realize that when you put 0 into the top and 0 into the bottom, you do get an indeterminate form of 0 over 0. And you don't have to write that down, but it is something that you want to get in the habit of doing that, especially when you start looking at actual AP tests where they will throw a simple one in every now and then. Once we've established that we do need to do L'Hopital, then we need to go through and do the derivative of the top and the bottom. So the derivative of sine is cosine, so we're going to have cosine of x over 2. And then you can't forget about the derivative of the angle. The derivative of the angle is just 1 over 2. On the bottom, the derivative of x is just 1, so we don't even have to write it. Now we're going to try a direct substitution, see if we're okay. When I put 0 in now, I'm going to get 1/2 times the cosine of 0. The cosine of 0 is 1, so my final answer is 1/2. The second one, this is an example of one that you could do algebraically, and I do not care which way you do it on a test. If you want to do it algebraically, you would rationalize. You would multiply by the conjugate on the top and bottom, which would be the square root of 25 plus x plus 5 over itself. I'm going to go through and do it with L'Hopital. First, double check. When you put 0 in, you do indeed get 0 over 0. So I'm going to take the derivative of the top, doing a quick chain rule. So power out front, power 1 less. Derivative of what's inside is 1, so I don't even need to write it. Derivative of the bottom is 1, so I'm not going to write that. So I've got 1 over 2 square root of 25 plus x. Now try direct substitution. I put 0 in. I get 1 over 2 times the square root of 25, which is 5. So my final answer is 1/10. I have seen problems, I actually took this problem from a practice AP test where it showed up on an AB test, and their expectation is you would do it with rationalizing. Because we know L'Hopital, we have another option. The last one looks a lot like one of the ones that's going to be on your test. Again, if you put 0 in, you do get 0 over 0. When you take the derivative of the top, you have to remember how to take the derivative of e to the u. You get the original e to the u times the derivative of the power. Derivative of 5x squared is 10x. And then on the bottom, the derivative is 6x. When you put 0 in, you still get 0 over 0. So you actually have a couple options for this. I'm going to take you through both and talk about what I think would be the most efficient. Your first option would be to then do L'Hopital again. So you could have to take the derivative. Now, the challenging part of that is if you look at this numerator, when you go to take the derivative again, you would have to do a product rule. And that's going to take some time. It's doable, but it's not really advised. What would be better, though, instead of going through all that, see if you can reduce your fraction. What you'll notice, and you might have noticed this already, your x's will cancel, and your 10/6 will reduce to 5/3. So you end up with 5/3 e to the 5x squared. Now, there's no need to do L'Hopital again because when you cancel those x's, it's no longer indeterminate. So now I can plug 0 in directly. E to the 0 is just 1, so I get 5/3 times 1, which is 5/3. I wanted to show that one because I wanted to show you that, yes, there are times that you have to do L'Hopital again, but before you do that, see if there are other options out there like simplifying so you can avoid that, because doing L'Hopital again would have required a product rule, which becomes very involved. It makes it very easy to make a mistake as you go through and do that. The last thing that we did with L'Hopital is we looked at limits that were indeterminate because they had an exponent that ended up either being 0 or infinity. We had like 1 to the infinity, 0 to the 0, infinity to the 0. This particular one, you end up getting infinity to the 0 power, because when you look at the bottom, 1 over x squared, as you go towards 0, this is just on the right side, but actually on either side, this one would be going towards infinity, and then when you put 0 in the exponent, you get 0. You do not need to write down or identify which indeterminate form, but you do need to recognize that that means that we have to use logarithms. So we're going to set this equal to y, take the natural log of both sides. So we have the natural log of y equals the limit, as we go from 0 from the right, of x natural log of 1 over x squared. At this point, a lot of times people ask, does it matter that it's a one-sided limit? It's not going to matter until you get to the end. When you go to evaluate that limit in the end, if you can't plug 0 in directly, then you have to deal with the one-sided limit. Prior to that, you do everything as normal. I need to write this as a fraction, so I'm going to write it as the natural log of 1 over x squared divided by 1 over x, using the reciprocal of x. When I put 0 in from the positive side, I do get an infinity over infinity. So I'm going to take the derivative. The derivative of natural log is du over u. Another option, if you don't want to go that route, you could actually use logarithm properties. So one option here is you could say, well, I'm going to rewrite the top as the natural log of 1 minus 2 natural log of x. So it gives you another option instead of going straight to the derivative. Natural log of 1 is 0. This might be a little easier to work with. So we have negative 2 natural log of x over 1 over x. When I do the derivative of the natural log of x, I get 1 over x. It still has a negative 2. You can put the negative 2 out front if you want. I have a 1 over x. The derivative of 1 over x is negative 1 over x squared. When I simplify that, I'm going to get 1 over x times negative x squared. One of the x's would cancel. This negative and this negative will cancel. So when it's all simplified, I get 2x. Now when I plug 0 in, I get 0. 2 times 0 is 0, so I didn't even have to worry about the fact that it was a one-sided limit. And then again, before you go and circle the answer or stop if it's a short answer, remember that in the very beginning, you took the natural log of both sides. So 0 is not our final answer. The natural log of y equals 0. Therefore, if I want to figure out what y is, which was my limit, I take e as the base on both sides, giving me a limit of 1. Now at this step, let's say you didn't use logarithm properties. That is completely fine. You can still do the derivative as du over u. The only thing that you'll have is you'll have a lot more x's to simplify, so it'll take a little bit longer, but you will get the exact same result. You'll still get 2x, whether you simplify with logarithm properties or you didn't at all and just went through a lot of the algebra simplifying. No matter what, you'll get the same result. You'll still get 0. You'll still take e on both sides and get 1. So you have a lot more flexibility with the logarithms in the way you simplify. Kind of like the last one, you had some flexibility with how you simplify. So you want to look for things like that maybe to make it a little simpler, but you can definitely go the longer route and still get the right answer. These 4 problems together, if you can do all of those, you'll be very successful on the test with all of the problems that deal with L'Hopital.